Welcome to Easy Academic. In today's video in the linear algebra series, we'll be covering vector addition and scalar multiplication. The definition of vector addition in linear algebra is simply, say we have a vector A, and we say that vector A is equal to A1, A2, where these are the entries in vector A. And we say that vector B is equal to B1, B2. We can say that A plus B will give us some vector C, where C is equal to the entries of vector A pairwise. So what that means is that we take the first entries of A, so A1, we add it to the first entry of B, which is B1. We then take the second entry of A, A2, and add it to the second entry of B, which is B2. And so what does this look like geometrically? If we were to draw a graph in 2 dimensions, and create 2 arbitrary vectors, let's now assign real values to A and B. So let's say that matrix A is equal to 2, 1. And then matrix B is equal to -1, 3. So first, if you'd like, you can pause to attempt to figure out what matrix C would be in this case. So if we took A plus B, we would find that C is equal to 2 minus 1 and 1 plus 3, which is equal to 1, 4. And so if we were to draw matrix A as 2, 1, so again that's 2 on the x and 1 on the y, like this. And matrix B, we'll do it in blue, and that's -1, 3, so -1 and then 3 in the y, so something like this. And I'll just draw in some negative values, -1, -2, -3. If we were to add these two vectors, we should get 1, 4. And so what we get is this vector C, which is equal to 1 in the x direction and 4 in the y direction. And so when we draw it out, it looks something like this. And so what does this exactly mean geometrically? Let's zoom in to get a better look. So if let's erase this for some clarity. If we took our first vector here, which is 2, 1, and then on the head of the first vector, we're supposed to draw the tail of the second vector. So instead of drawing the second vector from the origin, we draw it from the head of the first one. And so what we do is we go -1 in the x, we go 3 in the y. And so what we find is that we get this vector. And as you can see, this vector is exactly the same. This vector right here is exactly the same as this vector, but we've just drawn it at a different position. So what we're doing when we're adding vectors is we're really taking one vector and just shoving it on the end of another one. And so if we were to draw C now, by starting from the first place that the first vector starts at, which is the origin, and ending at the head of the second vector, we find we have the exact same vector, 1, 4, as we did when we drew it from the algebraic method. Let's now take the 3-dimensional example. Let's take the vector r, and we'll set its values to 1, -2, 4. We'll now take the vector s, and we'll set its values to 0, 5, -1. So if we now took r plus s, we'll find that it's equal to 1, 3, 3. Which, if you couldn't see that intuitively, it's 1 plus 0, -2 plus 5, 4 minus 1. With time, you'll be able to, with these simpler vectors, just add them up in your mind. And the same principle or property in 2 dimensions holds in 3 dimensions. So say we drew this out, we'd find that if we added this vector and this vector, what we would do is we'd add the tail of this vector to the head of this vector, and then find the resulting vector, and it would be exactly this vector, 1, 3, 3 in 3 dimensions. Now let's move on to scalar multiplication. So let's take the vector a. We'll set it equal to 3, -2. Now what scalar multiplication does, as I alluded to in the earlier episode, is that we've multiplied the magnitude of the scalar by a certain amount. So we multiply its length by a certain amount. So if we took this scalar value of 2 and we multiplied it by vector a, we'd find that 2a equals 2 times 3, -2. And you could write this mathematically as simply just the entries multiplied by the scalar. So 2 times 3 and 2 times -2. So we'd find that 2a is equal to 6, -4. Now geometrically, let's say we drew out, let's draw it in red. Let's say we drew out the original value for a. So we'd find that a is equal to 3 in the x, -2 in the y. So it'd be equal to this vector. So in theory, when multiplying by 2, what we'd find is that this vector that we get from this operation is in the exact same direction, but it's 2 times as long. And so let's see if that property holds. If we draw 2a in green, we should find that 6 in the x and then -4 in the y gives us this vector, which, as you can see, is exactly in the same direction as the original vector, but it's 2 times as long. If we take the same vector a, so a equals 3, -2, and we now multiplied it by a negative scalar. Let's say we multiplied it by -2. What we'd find is that -2 times a equals -2 times 3, -2 times -2. An interesting thing happens when you multiply a scalar by a negative value. So we find that the entries are equal to -6, 4. And so if we redraw the original scalar a, we'll find that we have 3 in the x, -2 in the y. What happens now is that the resulting vector from multiplying by -2 is pointing in the exact opposite direction. And so let's see if that holds true. So what we have is -6 in the x and 4 in the y. And so as you can see, this new vector points in the exact opposite direction as the original, and it's 2 times as big. Say we multiplied it by -1, it would just point in the opposite direction. And so what scalar multiplication does is it can make things point in opposite directions, and it can magnify the magnitude of a vector. And so this brings us to introducing the idea of linear combinations. So what happens when we combine vector addition and scalar multiplication? Let's say we have a vector, again a, and we set its value equal to 1, 2. And say we have a vector b whose value is equal to 4, -1. A linear combination is every possible way we can add a and b while multiplying a and b by some scalar values, c and d. And so what this looks like algebraically is we'll find some vector x, which is equal to c times a, so c times 1, 2, plus b times d, so plus d times 4, -1. And so what happens is that you can find any value for c and d and you can multiply it by these two vectors, and you'll be able to get any value x. In this specific case, an interesting thing happens, which is that A and B are not parallel. And so what that means is that they don't point in the same direction, or they don't point in exact opposite directions. And so what happens is that since these two vectors are not parallel, you can obtain any point in the xy plane. Let's say we had a new vector b, which was equal to 2, 4. What you might observe is that this is equal to 2 times a. Since a is 1, 2, if we multiplied it by 2, we get 2, 4. And so since it's equal to 2 times a, that means the two vectors are parallel. So if we now took this new b and multiplied it by, and took d and multiplied it by it, what we'd find is that every possible linear combination of a and b, so any value of c that we multiply by a plus any value d that we multiply by b, will simply get us a line, and that line has the direction equal to a or b. And so this is a preview into the concept of span in linear algebra, which we'll explore in a future video. If you have any questions, be sure to leave them in the comments. Thank you for watching, and be sure to like and subscribe for more related content.